So our last video is rather short because it's just learning how to calculate the pH of a weak base, which is almost the exact same process that we just learned about for a weak acid. There's just one extra very simple step to do. And so I'm going to do this whole problem on the slide since there's really nothing new. And I chose a problem from the book because I thought it was a very interesting wording. Find the pH of a 0.0372 molar solution of the commonly encountered weak base cocaine. And that, of course, made me wonder, And so it's an interestingly worded problem. So anyways, we have cocaine over here, rather complicated looking, and here's its conjugate acid, where the only difference is that H+ that the base has gained. So who wants to write all of this? We'll just say B for base and BH+ for its conjugate acid. And just like any other base, it takes that proton from the water and leaves behind hydroxide. And like what we saw before, we have some initial concentration. We know at equilibrium it will go down by some number x, and the conjugate acid and hydroxide will go up by that same value. And so from here, we just do the same thing as we did for a weak acid. We set up a K expression, and we get the value of Kb from the problem itself. Then we're going to small x, and then we're going to do some algebra, and it brings us to what we see here. Then we do more algebra to solve for x. In this case, the x value gives us our hydroxide concentration. And we're going to do a quick small x check, prove that it's less than 5%, which it is. And then we'll take that hydroxide concentration that we solved for and take its negative log to calculate the pOH. But the problem ultimately wants a pH, and this is where our one additional step comes in. We just take that value and subtract it from 14, which is the pKw. And we saw this relationship earlier in the lecture, and I said we'd learn it later when it was important for our examples. And so if there's one thing to write from this slide, it's that pH of a solution plus pOH must always equal 14.00. And we can prove that, but I'm not going to expect you to. But you're welcome to ask me in office hours or over email, and I can show you how that works. One final note, you might be wondering, why is there a pH when the reaction doesn't involve H+ at any point? And you have to remember that there are other equilibria occurring in this aqueous solution. Once this is formed, you've got a conjugate acid. It's going to donate protons to the water as well. We discussed that way back at the start of this lecture. Beyond that, everything is happening in water, which we know produces its own hydroxide and protons. So you will always have H+ and hydroxide in aqueous solutions, and thus we will always have pH and pOH, and they'd better add to 14, which is the pKw.